Good morning everyone, thank you for joining me for this video. It's going to be an additional video when we're talking about derivatives. It's an additional video on hyperbolics. You know, I've recently presented a video on exponential and hyperbolic function derivatives. Well, this is a video in addition to that, simply because I omitted a few items in the previous video saying that they are not important or that you may not see them frequently, and then I didn't bring them up at all. As you remember, I talked only about the derivatives of the hyperbolic sine, cosine, and the tangent. We know hyperbolic functions involve the exponential base, and we know that when we're talking about this hyperbolic sine function, it has the formula as you see here before you, and then the hyperbolic cosine has the formula e to the x plus e to the minus x over 2, and everything just basically in terms of deriving and derivation and the identity stems from these two terms over here. Everything stems from these two terms over here. It's important that when we're talking about hyperbolics, we identify some hyperbolic identities which are important, and I might have brought some of these up in the hyperbolic function video which I posted a while ago, but I'm going to go over those quickly again over here. Then we'll go into the derivative aspect of this video. Just like how trigonometric functions have their set of identities, there are a set of identities which accompany the hyperbolics. You don't have to go through all of them, but I'm only bringing the most important ones over here. One of the important hyperbolic identities is what I'm going to put over here, which demonstrates that the hyperbolic sine function is indeed a odd function. It doesn't have symmetry about the y-axis, it's an odd function. If you were to do this, you would know that it would equal this, just like the test you would do for an odd function, f of minus x is equal to minus f of x, and you could prove this out too. So let's quickly do that. If you're looking at the terminology or the definition of the hyperbolic sine, you know it looks something like this. But if you were to plug in these minus x's over here, you would actually put the minus x right in here. You would plug in this minus x in place of x, and this is what you would get: e to the minus x minus e to the minus x. You see over here, you plug in a minus x as well over 2, and when you were to do the algebra over here, you'd get e to the minus x minus e to the x over 2. Now this right here is this first part plugged in. Now if you look at this, we have to show that this thing is equal to that. If you take the very basic hyperbolic sine definition, which is e to the minus x, e to the x minus e to the minus x over 2, and now you multiply this by a minus 1, which you have to show over here, it affects the arrangement of this numerator over here. What you end up getting is e to the minus x minus e to the x over 2. Look over here. These things flip around because of the minus effect, and you get this e to the minus x minus e to the x over 2, and you can see both of these things are the same. So you have this item over here placed and run over here, and you have this over here. So you're showing both of these are equivalent. So this proves this one identity of this hyperbolic sine, that sine hyperbolic function is indeed a odd function. Now let's look at the specific identity which applies to the hyperbolic cosine function, which proves this to be an even function. The hyperbolic cosine function is an even function. It'll have symmetry about the y-axis. If you look at this specific identity and you plug in minus x, you'll prove the even test where f of minus x is same as f of x. That's the test for the even function. So all you have to do is just basically look, the hyperbolic cosine function in terms of x is just equal to e to the x plus e to the minus x over 2. But when you look at this right here, cosine hyperbolic, in terms of the minus x, you get e to the minus x, because now you're plugging in minus x plus e to the minus x over 2. When you simplify this, you get e to the minus x plus e to the x over 2. And if you just flip these things around, the plus sign in the numerator, you get e to the x plus e to the minus x over 2. And now this over here and this over here, results are the same. So you've proven over here that hyperbolic cosine function is an even function. It is an even function because it passes this even test. So this is another identity for you to remember, another hyperbolic identity. Let's look at some more identities before we get into some of the derivatives. And we'll be talking about the derivatives of those hyperbolic functions that I missed, which I purposely didn't talk about. The hyperbolic cotan, hyperbolic secant, and the hyperbolic cosecant. Many of the identities, and there are many identities for hyperbolics, they mirror to some degree the trigonometric identities. Many of them look quite same or similar, but they're not exactly the same. If you remember clearly the Pythagorean identity for the trigonometry, it was sine square x plus cosine square x is equal to 1. And this is an identity similar to this, which I brought up in the yesterday's video about the hyperbolic and exponential derivatives. And that identity was this: hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. This right here is a hyperbolic identity version of this for the trigonometric. So when it comes actually to proving this hyperbolic identity, and it is a subject that I've shown you in my hyperbolic function video, and I'll do it again, you just have to basically incorporate their basic function definitions for each of these, and this is how you would proceed. Hyperbolic cosine looks like this in terms of its definition, and you have to square it because you got a square involved over here, and then you have to do the same with the hyperbolic sine, which is e to the x minus e to the minus x over 2, and you got to square this as well, and then you got to carry this out to completion. You basically do this multiplied by itself minus this thing multiplied by itself, and you can do it all in a very expedited manner because both of these 2's will become 4's, and you'll have a minus here which you can just comfortably bring down. You're going to basically open this part here and open this part here, and I'm going to do it all in one step. Let's look over here. E to the x times e to the x is e to the 2x. Then you'll have this intermediate term kick in, and you can do this separately on the side. 2e to the x, e to the minus x, and then you'll have plus 2e to the minus 2x. And this is not going to be a plus 2, it's going to be e to the minus 2x. E to the minus 2x. Now as we open up this with terms, with this multiplying it with itself will affect it with a minus sign. You'll basically have a minus e to the 2x. You'll have a plus 2e to the x, e to the minus x. Remember, you can do this on the side on your paper. You'll have this minus e to the minus x multiplying by minus e to the minus x. It will become positive e to the minus 2x, but it'll get affected by that minus. It will become minus e to the power of minus 2x. I was going to put that 2 again over here. Anyhow, we're good. Now you have to look for terms which are cancelable. Look over here, e to the 2x, e to the 2x, e to the minus 2x, and then minus e to the minus 2x. And these individual reciprocals will cancel out with each other. In essence, what I'm trying to say is you get 4 on the top and 4 on the bottom, and you get 1 as your final answer. So you end up proving that this hyperbolic identity, hyperbolic function identity, hyperbolic cosine squared x minus hyperbolic sine squared x is indeed equal to 1. So it's a very important identity, a very similar identity to this, but you've seen this in action in my video which I posted previously in the hyperbolic and exponential derivatives, and you can see this play out a number of times in the questions that you will do on your own. It's too important of an identity to ignore. We'll look at 2 more other important identities similar in appearance to this but with the different functions. When you look over here at this is one of those Pythagorean identities which come in trigonometry, but there's an equivalent such identity when it comes to hyperbolic functions, and the identity is this: 1 minus tan hyperbolic tan square x is equal to hyperbolic secant square x. That's your identity. But we're talking about not just simply this, we're talking about how do we actually come up with this. The arrival of this identity comes from the very previous identity, which was this: cosine hyperbolic square x minus sine hyperbolic square x was equal to 1. If you divide everything here by the hyperbolic cosine function squared, if you divide it out and you simplify it, look what you do. When you simplify it, you separate things out. Look what you'll get. You'll get cosine h squared x divided by cosine h squared x minus sine h squared x over cosine h squared x is equal to 1 over cosine h squared x. Now look over here, in the arrival at this equation over here, or this expression over here, when you cancel this out, you're getting a 1. When you look over here and you rewrite this in a more friendly format, you get tan h squared x, because tan is a function made of the sine or the hyperbolic sine divided by hyperbolic cosine. And this right here is equal to hyperbolic secant squared x. So you're arriving at the same item over here. So when it comes to the trigonometric function right here, this right here is the hyperbolic version of that same, except it's slightly different, but this is how you derive it. So this is another identity over here you should be very familiar with. It can pop up in these derivative questions. Now let's look at this one right here. This right here is a trigonometric identity I've presented to you in my trigonometric videos. But just like you have this as a trigonometric identity, one of the Pythagorean identities, there's a very similar identity in terms of the hyperbolics, and the identity looks like this. Hyperbolic cotan square x minus 1 is equal to hyperbolic cosecant square x. This right here is the identity you want to be familiar with. And the derivation of this comes exactly from the previous identity, the parental identity, which is this. Hyperbolic cosine squared x minus hyperbolic sine squared x is equal to 1. When you divide everything here by the hyperbolic sine squared x and you simplify it out, you'll get to this. But let's do it. You'll get hyperbolic cosine squared x divided by hyperbolic sine squared x minus hyperbolic sine squared x. It's like a mouthful saying these words. Hyperbolic sine squared x is equal to 1 over hyperbolic sine squared x. Now look over here. This thing cancels out and you get a 1. This over here, cosine divided by sine, or the hyperbolic versions, is equal to hyperbolic. And look over here. You're getting a reciprocal of the hyperbolic sine, which you know will be the hyperbolic cosecant. And you get exactly the same hyperbolic identity. So remember these identities you need to be very familiar with, and I've put them out for you, and I'll put them here again. The identities are this: hyperbolic cosine squared x minus hyperbolic sine squared x is equal to 1. And then of course the one you see over here, hyperbolic cotangent square x minus 1 is equal to hyperbolic cosecant square x. And this one right here, 1 minus the hyperbolic tan square x is equal to hyperbolic secant square x. So these are the three hyperbolic identities, perhaps the three most important ones you need to be familiar with. Now let's get into the actual discussion of derivatives for those remaining three which I did not present in the previous video. So when I did the previous video, I only talked about these three and I omitted the remainder three, and then I came to thinking that just for the purpose of completeness, maybe I should have talked about the other ones, even though you may not see them as frequently, but it wouldn't hurt to talk about them. And you know the ones which I'm talking about are the hyperbolic cosecant, the hyperbolic secant, and the hyperbolic cotangent. So let's look at those three in terms of their derivations, and then we look at a few examples, and that'll be the substance of this video. So let's start with the hyperbolic cotangent. If someone asks you to derive the derivative of this hyperbolic cotangent, how would you proceed? Well, this is how you would proceed: by converting into a rational function, because you know the hyperbolic cotangent is made of the quotient of these two functions, and then you know you can use a quotient rule, and you can do that. You'll use a g function and you'll hit that with the derivative, and there's nothing new we're talking about here. Hit that with the derivative of your f function. This right here is your f, and this right here is your g, minus the original f function multiplied by the derivative of the g function, which we have to actually do, we're just laying it out, divided by the g function squared. So let's do some computation over here. The hyperbolic cosine derivative, as you see over here, is just a sine. So sine h times sine h, you get sine h squared x. You can see that. The derivative of this is a hyperbolic cosine, which multiplies with the same, and you get hyperbolic cosine squared x over sine h squared x. Now you're thinking, like, what do we do over here? This is where you look over right over here at this very first identity. It's everything is the same except it's flipped around. So if you were to multiply everything over here by a minus 1, if you were to hit everything by a minus 1, you can exactly end up with that, and you would end up with this. You'll get minus 1 times hyperbolic cosine squared x minus hyperbolic sine squared x over hyperbolic sine h squared x. And now this right here becomes a 1. It cancels out to a 1. The numerator, this aspect right here, becomes a 1 based on that identity. 1 times that minus 1, you get a minus 1 over sine h squared x, which you know if you simplify this, you'll get your answer. The derivative of this would become minus cosecant h squared x. Minus cosecant h squared x. So that would be the derivative of this hyperbolic cotan function. Now we are tasked with finding the derivative of, let's just say, hyperbolic secant function, and you know you can rewrite this in terms of its reciprocal function 1 over this, because you're converting things into familiar terms, sine and cosine hyperbolics, because you know what they are. And you proceed with this using the quotient rule. You do the g function and you have the f function. The g function multiplied by the derivative of the f function, which you know is just a 1, which will zero out, minus the original f function multiplied by the derivative of the g function, which you have to show, divided by g squared, the hyperbolic cosine squared x. Look over here, derivative of 1 or a constant is 0, all of this will zero out. You still have the minus here on the top. Minus 1 will multiply by the derivative of the hyperbolic cosine function, which will give you a sine hyperbolic function, divided by cosine h squared x. And I'm going to rewrite this by spreading things out. Look, I'm going to spread things out. Divided by cosine hx times 1 over cosine hx. Now look over here. My final answer will be just this rewritten in a different way. Minus sine hx divided by cosine hx is a minus tan hx, and 1 over cosine hx is just a secant hx. Now look over here, here's your final answer. The derivative of hyperbolic secant function is minus hyperbolic tan function times hyperbolic secant function. It's very close to the derivative of the secant trigonometric function. Remember, derivative of the secant was tan theta secant theta, or secant x tan x. Here, instead of secant x and tan x, we have a minus involved, and we have hyperbolic tan times hyperbolic secant. It's very close to that. And look over here, this is also very close to this trigonometric derivative of the cotan function. Remember, the derivative of the cotan function was just a minus cosecant square x. Here we're getting a minus cosecant h squared x, a hyperbolic version of that. So keep all of these things in mind. We just have one more to talk about, the hyperbolic cosecant, then we'll go into few actual examples, alright? There won't be too many examples for this video because we're talking about some of the hyperbolic derivatives which are not very frequently seen. Let's look at the derivation of the hyperbolic cosecant function, and you know it's going to follow a very similar scheme of deriving as what we have done. You'll convert this into its reciprocal, which is a 1 over sine hx, because you have a familiarity with that. And then you use the quotient rule. You do the g function. Here's my f over here, here's my g over here. You do the g function multiplied by the derivative of the f function, which will just be a 1, which will become a 0, of course, multiplied by the f function, and minus the f function multiplied by the derivative of the g function, which we have to still see, over the g squared sine h squared x. This derivative of a constant is 0, all of this zeros out, so it's good. On the top you get a minus 1 times the derivative of hyperbolic sine, which is a hyperbolic cosine, and you dividing this by hyperbolic sine squared x. Here you're doing exactly the same thing as separating them out as you did in the previous question. When you're separating them out, it makes sense because you break it down into its easier format. You get over here a minus cosine hx divided by sine hx multiplied by 1 over sine hx, because if you went backward from here to here, you'll end up with exactly what you have. But we're rewriting things out over here, and what do we get? You'll get a minus cotan hyperbolic multiplied by cosecant hyperbolic x. And if you think back to the derivative of the cosecant x, the trigonometric cosecant x, it was equal to, if I remember correctly, it was equal to minus cotan x cosecant x, and the hyperbolic very much mirrors that. So this has been derived, and we can remember this, or we can put it on our cheat sheet. I'll probably put it down here, and then we can look at some examples. But I guess maybe I might erase all of this and just use my cheat sheet, because I might need space for my questions. But keep all of this in mind. Keep this one over here in mind. Keep all of these over here in mind. The identities here, 3 on the top, and the derivatives over here, 5 over here, and here's our 6. So keep all of this in mind. But let's look at a few examples and then we'll wrap it up. So in the remainder of this video, we'll be looking at 4 examples. Therefore, we will be having some fun over here. As needed, I'll present the derivative of that function as it comes into play. But we're looking at this question over here, x times hyperbolic cotan in terms of this. And we know we have a product rule kicking over here because we have 2 different functions. But within this product rule, we'll have a chain rule because we'll have to make a substitution over here. So let's proceed with the product rule. F function, g function, you're going to do the g function in its entirety multiplied by the derivative of the f function. And then you'll add the f function and its product with the derivative of the g function, 1 plus x squared. This right here is where a substitution will come into play. Because we have a composite function over here, if u is equal to 1 plus x squared, then f of u is equal to hyperbolic cotangent in terms of that u. And we know the derivative of hyperbolic cotangent, the derivative of hyperbolic cotangent x is equal to minus cosecant h squared x. So let's proceed with this substitution. We'll come back over here. The hyperbolic cotan in terms of that 1 plus x squared multiplied by the derivative of x, which is just a 1, plus x times the chain rule will kick in over here. Hyperbolic cotan u, look over here and over here, times du over dx, which is 1 plus x squared. Now we come over here, hyperbolic cotan times 1 plus x squared, nothing to be done over here because it's all nothing you can do over here. Plus, let's do the derivative of 1 plus x squared, which will just be 2x. Polynomial derivative, easy. 2x multiplied by this x, you'll get a 2x squared multiplied by the derivative of this, which is a minus cosecant hyperbolic squared u. Don't forget that u over here. Now, we have cotan hyperbolic times 1 plus x squared, well not times, but it's part of it, is attached to it, plus, we should convert this plus to a minus. Why? Because this minus will hit that positive and make it a minus 2x squared, and let's bring in the substitution of this u back, which is 1 plus x squared. Look, this is what we're getting over here, and this over here will represent a complete and good answer. It was not a hard question, but it was a good question. Let's look at another example. So our question is this. If you're looking at it, we should not get confused into the idea that this is a product rule type of question. It isn't. It isn't because all of this is one function over here, but it's a composite function. Because this ex lies within the parentheses that is affected by this hyperbolic secant function, which is to the square. So we might have like a double chain rule maybe come into play. So we have to actually start here with a substitution because this is a chain rule type of question. Our substitution would be if u is equal to secant hyperbolic e to the x, then f of u must be equal to u square, and we have to proceed with that. You have a u square and then the derivative of that u with respect to its variable secant h ex. But look over here, we still have a composite effect over here, so we must do another substitution over here. The other substitution we will do is v is equal to e to the x. Therefore f of v must be hyperbolic secant h with regards to that v, or of that v. And that's exactly where this other substitution will come into place. It will play out like this. Derivative u square and then du with regards to dv, we have secant h v, and then dv with regards to dx is going to be e to the x. Now let's put over here what the derivative of a hyperbolic secant function looks like. It looks like minus exactly what I put over here, minus hyperbolic secant times hyperbolic tan. That right there is what we have to keep in mind. Let's do our actual derivative part over here. U squared will become a 2u. Secant hv will become all of that minus secant hv tan hv, because we have to substitute in place of these u's and the v's. And the e to the x by means of that exponential format stays as is. Remember, it was e to the ax. In a very simple case, this right here, a simple case becomes a e to the ax, and this stays as e to the x. Easy. Let's bring the exponents together, or let's talk about the coefficients. Minus in this 2 becomes a minus 2. Let's bring the e to the x closer to the beginning. We have a u. Let's substitute for that u, which is this secant h e to the x, and then let's bring in these over here with their v components substituted back. We'll have a secant h to the ex, where v represented e to the x, and tan h e to the x. Now look over here, we have a common term over here which can be multiplied together because they're multiplying together. Our final answer will be minus 2e to the x secant h squared e to the x, because these are two similar terms multiplying. You bring the exponent times tan h e to the x, and you would be done. This right here would be your final answer. A good answer. Our question is this. Looks like a tricky question, but it isn't. If you're looking at it, you're thinking about the product rule. You have one function over here and you have one function over here, and you would be right. It is basically the product rule here coming into play, and we know the derivative of the cosecant hyperbolic function is equal to minus cosecant hx times hyperbolic cotan. Let's proceed here using the product rule template. And the product rule template by now you are all familiar with is a g function multiplied by the derivative of what will be, which we will do that in the next step, the f plus the f function in its originality multiplied by the derivative of what will be of this g function. And you have to proceed with this right here remains unchanged. 1 minus cosecant hx will multiply by with the derivative of this, which right here you have to rewrite over here, minus cosecant hx hyperbolic cotangent x plus cosecant hx times the derivative of this. Basically the derivative of 1 is just a 0. You're basically now looking at just the derivative of minus this. If the derivative of hyperbolic cosecant is minus that, then the derivative of minus that will positive that. It'll negate the minus, and you'll just get hyperbolic cosecant x times hyperbolic cotangent x. You'll see that. Now you gotta do is multiply things together. You have this expression multiplying with all of this, so you have to do that. You'll have a minus cosecant hx cotangent x, because I'm multiplying this 1 with this item, then I'm multiplying this with that item. And this minus hyperbolic cosine part will multiply with this minus, and you get a plus over here. You get a positive. But see, this hyperbolic cosecant and the hyperbolic cosecant will bring a square over here, and it'll still remain attached to this hyperbolic cotan function. Now you have just one item multiplying with another single item. It's a single item still, and you get a hyperbolic cosecant squared x and hyperbolic cotangent x. Now look over here. Are there commonalities we can see? This right here is the same thing as this right here. You're doing like essentially 1 plus 1. You're getting like a 2. You're doubling it. So let's rewrite everything in a more close to a final format. You get plus 2 hyperbolic cosine squared x, hyperbolic cotangent x. Now look over here. We have commonalities here, things you can isolate. We have a hyperbolic cosecant, hyperbolic cotangent, and similarly we have over here. Let's isolate a hyperbolic cosecant x and a hyperbolic cotangent x, and then it goes in here minus 1 times, and it goes in here plus 2 cosecant hx times. But I'm going to write this in a better way with the minus second and the positive aspect first. I'll rewrite it as this, and I'm bringing it out here for you to see. 2 cosecant hx minus 1, and this right here should be a final answer. So this right here serves as our very last question. We have a rational function over here, so we know we are bound to do the quotient rule, but we also have a composite function over here, so we will be bound to do the chain rule as well. When it kicks in, we'll do the chain rule. So let's proceed over here. Let's do the template for the quotient rule. We'll start with the g function, which will multiply by the derivative of what will happen to be a chain rule coming into place over here eventually, minus the original f function multiplying by the derivative of the g function, and this is going to be an over x square, because the x follows the g square format. It becomes x square. Now we have to do a substitution over here. If u is equal to square root of 1 minus x squared, then f of u is equal to secant h u. And I'll talk about the actual derivative when the time comes. So let's lay it out. X times derivative of u, you get a secant h u, and then du with regards to dx square root of 1 minus x squared. Now let's make a little halt over here, because I know I still have a composite function over here. In the interest of space, let's get to that. An extra kink right away. If v is equal to 1 minus x squared, we know f of v is equal to root v. So let's bring in this extra kink right here. So derivative of u with respect to derivative of v. Now you're going to put root v over here, and then derivative of v with respect to its variable 1 minus x squared. This right here is all of this part right here before the minus sign. Now let's go to the minus sign. secant h square root of 1 minus x squared times the derivative of x, which will just be a 1. We can just forget about that and we'll have a 1 over here. This right here is all over x squared. Now let's do the actual derivative part over here. X will multiply with the derivative of hyperbolic secant is minus hyperbolic secant and times hyperbolic tan. And when I lay it out, you'll see a minus hyperbolic u of secant multiplied by the hyperbolic tan, and then we're still keeping the u's over here. Derivative of root v, as you know, is a 1 over 2 root v. We've seen this too commonly play out, this type of thing. 1 minus x squared is really a minus 2x. And then we have this minus secant h square root of 1 minus x squared. And now you know all of this over here is dividing by this denominator of x squared. I'm just writing here on the side due to space limitations. Let's do simplification. This 2 over here, well, it divides actually with 2. And you see this minus over here? This minus will cancel out with this minus over here. You cancel it out. What do you have left on the top? You have this x and this x. You get an x squared. And then you have this secant hu and then tan hu. So let's resubstitute back. Secant hu was square root of 1 minus x squared. Tan hu, the hyperbolic tan, and its u value right over here, square root of 1 minus x squared, all over root v. And what was root v? What was v? 1 minus x squared. 1 minus x squared minus this part over here, secant h square root of 1 minus x squared. And you know all of this right here, all of this is over an x squared. Now let's do some expedited simplifications over here. You can separate everything out under its individual denominators. Let me show you. I'm separating everything out under their individual denominators. And we're going to do everything over here cleanly, but we're separating things out. See? Over x squared. When you're separating things out like this, see, I've individually separated the denominators. They both originally had a denominator of x squared. I've just kept the denominator the same, but I've separated them out around the minus sign. Now let me show you. I'm going to write this better. I'm going to bring this x squared right over here because it technically is right over here under x squared. And now look over here. This x squared is really an x squared over 1. If you did a fractional flip, this thing would come right over here. X squared would come right over here. I'm not doing anything fancy over here other than I'm using the space limitation I have, and I'm showing you the arrival at the final answer. This right here is very close to final answer except for one thing. You have an x squared over here, you have an x squared over here, you can cancel them out and now write your final answer. Hyperbolic secant to its 1 minus x squared multiplied by the hyperbolic tangent to its 1 minus x squared divided by square root of 1 minus x squared, this minus right here, and then the hyperbolic secant to its 1 minus x squared and divided by its x squared, which never cancelled out, which is fine, it never cancelled out. This right here is your final answer, and it's right, a good final answer and a good question. So this wraps up my presentation on these additional hyperbolic features that I wanted to talk about. The only thing new over here was I presented those 5 additional identities, 3 of which were the very important ones, the ones which kind of mirrored the Pythagorean trigonometric identities. The other 2 identities, the hyperbolic identities, were which demonstrated that the hyperbolic sine was an odd function and the hyperbolic cosine was an even function. But in addition to those 5 hyperbolic identities, I presented the new derivatives of the hyperbolic secant, the hyperbolic cosecant, and the hyperbolic cotangent functions. Now you know things can get pretty crazy. Just like I've talked about inverse trigonometric ratios, inverse trigonometric functions, as they are inverse for the original, there are actually such a thing called inverse hyperbolics, and you'll have inverse hyperbolic derivatives. It may be a topic I might go into or I might not go into, I'll have to see. But the inverse hyperbolic derivatives, their derivatives are actually very close to the inverse trigonometric. But even if you don't go into that topic, it's fine. You can always use your cheat sheet and run through those types of questions yourself. All I'm just trying to say is that the inverse hyperbolics are not as important as regular hyperbolics, and you just don't see those questions applied very frequently at all. So it may be a topic we might omit entirely. And I'm saying the inverse hyperbolic derivatives, alright? Those are topics we might omit entirely, but I'll decide later on. But that's the end of this video. I hope you enjoyed this video. Please stay tuned for more videos coming up. Thanks.